Okay, this is the second of a two-part video where we look at the Catalan numbers. So part one is on the YouTube channel Professor Omar Math. So I urge you guys to check out part one of this video. A link is in the description. In his video, he gave a combinatorial description of these numbers as well as a recursion which these numbers satisfy. So part two of this video is obviously here. We're going to construct a generating function and describe a closed form of these numbers. So just to pick up where he left off, the Catalan numbers can be defined in the following way. So C0 is equal to 1, and then Cn plus 1 can be defined in terms of C0 through Cn in the following sum. So we have the sum as I goes from 0 to n of Ci times Cn minus I. So notice that's going to be the sum where the first term is raising in its index and the second term is lowering in its index. So here we have C0 Cn, C1 Cn minus 1. The next one would obviously be C2 Cn minus 2 all the way up to Cn C0. Okay, so since our goal is to find a generating function in a closed form, we're going to need a couple of tools, which I will sketch the proof to why these things exist. So the first one will be this following sum, which is called the Cauchy product of two series. So we have this infinite power series ai x to the I and then one which is bj x to the j, and if we take their product we get this infinite sum k equals 0 to infinity of this finite sum L equals 0 to k of a sub L times b sub k minus L and then times x to the k. Okay, so we'll go over that first. And then the next one that we will need is this binomial coefficient identity. So if we look at 1/2 choose n, we have that is equal to minus 1 to the n plus 1 divided by 4 to the n times 2 to the n minus 1 times this thing which is known as a central binomial coefficient, which is 2n choose n. Okay, and then next we will need another binomial coefficient identity, which is 1 over 2 times 2 to the n plus 1 times 2n plus 2 choose n plus 1 is the same thing as 1 over n plus 1, 2n choose n. Okay, so now that I've laid out what the Catalan numbers are, let's get to proving these identities, but first we need to clean up this board. Okay, so I've laid out an array for explaining why this Cauchy product is true. So notice along the top row I have my first power series. So I have a0 plus a1x plus a2x squared plus a3x cubed. And then on my leftmost column I have the power series with the b sub j coefficient. So I have b0 plus b1x plus b2x squared, b3x cubed, and so on and so forth. And so if I want to multiply these, it will be just like multiplying all the rows and columns, if you will. So notice in this spot I'm going to get a0 b0, and then in this spot I'll get a1 b0 times x. Here we have a2 b0 times x squared. Here we have a3 times b0 x cubed. Okay, and now we can fill in the rest of this array in a similar way. And here notice I'm going to put plus dot 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 because that's an infinite sum. And now down here I will get plus a0 b1x plus a0 b2x squared plus a0 b3x cubed, and then all the way down. And now I just need to fill in the middle. Okay, so now in this next row I have a1 b1x squared because I have x times x is x squared, and then plus a2 b1x cubed plus a3 b1x to the fourth dot dot dot, and then I have pluses going this way as well. And now I can continue on. So I've got two more rows to do in order to get like a nice picture here. So here I'll have a1 b2 x cubed, a2 b2 x to the fourth, a3 b2 x to the fifth, and so on and so forth. And then finally down here, I'm going to have a1, b3, x to the fourth, plus a2, b3, x to the fifth, and then finally a3, b3, x to the sixth, plus dot, dot, dot. Okay, great. So that gives me some sort of idea for how this is going. But now if I look at my diagonals going this way, I can see common powers of x. So notice everything on this diagonal is x to the 0th power. Everything on this diagonal is x to the 1st power. Everything on this diagonal is x to the 2nd power. Here we have x cubed, and then so on and so forth. So x to the 4th is going to extend up here, and then extend down here, and then we keep going and going and going. So notice that tells us that this product will be a0, b0 plus, now I'm going to factor an x out of this. So we have a0, b1 plus a1, b0 times x. And then I can factor an x squared out of this term. So I have a0, b2 plus a1, b1 plus a2, b0, x squared, and then so on and so forth. Okay, great. But notice that these coefficients clearly have this form right here. So notice we're summing over all products here where these two indices add to k. Notice L times k minus L is k. And that's exactly what's happening right here. We're summing over all indices that add to 1. That's the coefficient of x to the 1st power. All indices that add to 2, that's the coefficient of x squared, and so on and so forth. Okay, good. So I think we've argued this well enough, and now we're ready to move on to the next one. Okay, so now we're going to move on to the second bullet point that we need to prove. And we're going to do this by starting at the right-hand side, using the definition of the binomial coefficient, and then simplifying it until we get the left-hand side. So let's start with minus 1 to the n plus 1 over 4 to the n times 2n minus 1. And then we have 2n choose n. Okay, and so by the definition of the binomial coefficient, I can write that as 2n quantity factorial over n factorial and then 2n minus n factorial, but that's just going to give me another n factorial. So that's good. And then I'm going to rewrite minus 1 to the n plus 1 as minus 1 to the n minus 1 because those are clearly the same number. N plus 1 and n minus 1 have the same parity. And then I'm going to write 4 to the n as 2 to the n times 2 to the n. And then we have this 2 to the n minus 1 left. Okay, great. Now I'm going to expand some of these parts out into a product. So I'm going to write this thing as minus 1 to the n minus 1 over, now we have this 2 to the n times 2 to the n times 2 to the n minus 1. And now let's write this 2 times n factorial as a descending product. So we have 2n times 2n minus 1 times 2n minus 2 all the way down to 4 times 3 times 2 times 1. So there, that numerator is 2n factorial. Now I'm going to take one of these n factorials and I'm going to write that as a descending product as well. So I'll write it in the following way. I'll have n times n minus 1 times n minus 2 would be next, all the way down to 2 times 1. So I've spread those out for a reason that we'll see in just a second. And then I have one thing left over. I have 1 over n factorial left because I haven't done anything with that. And now we can do some simplification. So notice this guy is going to cancel this guy and turn it into a 2. This guy is going to cancel this guy. It's going to turn it into a 2. All the way down, we get a 2 there, and this guy cancels that into a 2. The last one obviously doesn't really cancel. And then how many 2's do we have on the top? Well, notice we'll have exactly n 2's on the top, and that's going to cancel this 2 to the n in the denominator. So we'll have all of these cancel this guy right here. Okay, good? And then also we have this 2 to the n minus 1, which is going to cancel this 2 to the n minus 1 as well. Okay, so now let's see what we have. We have minus 1 to the n minus 1 over 2 to the n. Okay, and notice this thing is going to pick up here at this point that I haven't written, which is 2 to the n minus 3. And now I'm going to write this as a rising product instead of a falling product. So I can start 1 times 3 times 5 all the way up to 2n minus 3. Notice all that's left are the odd numbers. So I have 1 times, I'm actually going to put another 1 in there, which will be clear a little bit later while I'll do that. So I have 1 times 1 times 3 times 5 times 7 all the way up to 2n minus 3. And then this is all over n factorial. So one important thing to notice here is that now that I've added this 1 in, there are exactly n terms in this product. So what I'm going to do is I'm going to take the n terms of them in that product, and I'm going to put them all over 2 using this 2 to the n, which is in the denominator. So that's going to give me negative 1 to the n minus 1 over n factorial. And then that will be multiplied by 1/2 times 1/2 times 3/2 times 5/2 all the way up to 2n minus 3 over 2. So that will be my last term. Okay, so on the last board we worked our calculation to here. So we have minus 1 to the n minus 1 over n factorial, and then 1/2 times 1/2 times 3/2 times 5/2 all the way down to 2n minus 3 over 2. Now what I want to do is notice that I have a product of n terms in the top, in this right-hand bit, which means there are n minus 1 terms if I leave off the first half. And so what I'll do is I'll take this minus 1 and I will include it in those n minus 1 terms. So that's going to give me the following. So I'll have 1 over n factorial times 1/2 times minus 1/2 times minus 3/2 all the way down to 3 minus 2n over 2. Okay, good. But now let's notice that this is the following. So this is going to be 1/2 and then 1/2 minus 1. So we can write negative 1/2 obviously is 1/2 minus 1 times 1/2 minus 2. So negative 3/2 is obviously 1/2 minus 2 all the way down to 1/2 minus n plus 1. So this 3 minus 2n over 2 can also be written as 1/2 minus n plus 1. So I'll let you guys check that. It's fairly easy to see. And then I'll put this all over n factorial. But let's see what we have here. We have a falling product of n terms starting at 1/2 over n factorial, but that's exactly the definition of the binomial coefficient 1/2 choose n. Okay, good. So that finishes the proof of this next bullet point. Okay, so now we're ready to move on to our third bullet point, which is the last of our 3 tools which we will really need to get a closed form of the Catalan numbers via a generating function. So I'll also do this just by direct calculation. So notice I have 1 over 2 times 2n plus 1, and then we want to multiply that by the binomial coefficient 2n plus 2, choose n plus 1. So that's one of these central binomial coefficients. I may make a video about just the central binomial coefficients later. They have some nice properties on their own. Okay, great. So from here, we can write this as 1 over 2 times 2n plus 1. And now this is going to be 2n plus 2 factorial over n plus 1 factorial times n plus 1 factorial. Okay, so that's just using the definition of the binomial coefficient. And I shouldn't really say the definition, but the special case of the binomial coefficient where we have a natural number. The definition is actually closer to what we saw with 1/2 choose n on the last board. Okay, so now I'm going to pull some stuff out. So in fact, what I want to do, I'll write this as 1/2 and then 2n plus 1. And now I'll write this as 2n plus 2 times 2n plus 1 times 2n factorial. And then I'll rewrite those 2 factorials in the denominator as n plus 1 times n factorial and another n plus 1 times n factorial. And now let's see what simplification can occur. So notice this 2n plus 1 is going to cancel that 2n plus 1. Okay? And then notice that this 2 times n plus 1 is going to cancel this 2n plus 2. And that's going to give us exactly, after we pull this out, 1 over n plus 1 times 2n factorial over n factorial n factorial. Great. But that's exactly what we need it to be, i.e. that is 1 over n plus 1, 2n choose n, which finishes the proof of this third part. Okay, so now I'm ready to go on to something that's more of my main goal, which is to build a generating function for the Catalan numbers and use that to find their closed form. And so let's go ahead and set c of x equal to the generating function of the Catalan numbers. In other words, the sum n equals 0 to infinity of cn times x to the n. So our goal will be to find a closed form for this generating function and then re-expand it as a power series where we can see a closed form for the Catalan numbers. So let's see how we can do that. So what I will start with is by pulling the first term out. So notice the first term will be n equals 0, so we have c sub 0 x to the 0. So that's obviously just the number 1. And now I have this is going to be plus the sum n equals 1 to infinity of cn x to the n. But now to make this look exactly like our recursion, I want to re-index so that I have an n plus 1 there instead of an n. So in other words, I'm going to send n to n plus 1. And that's going to change my start from n equals 0 to from n equals 1 to n equals 0. So that's going to give me 1 plus the sum n equals 0 to infinity of cn plus 1 times x to the n plus 1. So the next thing that I want to do is take an x here from this n plus 1 and factor it out. So notice that's exactly the same thing. If I distribute this x through, I'll get x to the n plus 1. Now I want to use my recursion, so this is going to be 1 plus x times the sum n equals 0 to infinity of the sum I equals 0 to n. Here I'm using my recursion for the n plus first Catalan number, which was derived in the previous video. And then we have ci times cn minus I times x to the n. But now what we want to do is notice that this looks really, really similar to something that's happening in our first bullet point, which means that we can write this as 1 plus x times the sum, maybe m equals 0, the sum maybe L equals 0 to infinity of CL x to the L times the sum M equals 0 to infinity of CM x to the M. Okay, good. So notice this product is going to be the same thing as this infinite sum by this first bullet point, but notice each of the terms of this product are just the generating function of the Catalan numbers with the indices renamed. So this is exactly equal to 1 plus x times c of x squared. Okay, so now that we have this nice fact, we are close to getting a closed form for the Catalan numbers. I'll clean up the board and then we'll move on. Okay, so let's see. So far we see that c of x equals 1 plus x times c of x squared, where c of x is the generating function for the Catalan numbers as we described on the last board. So notice that's going to give us the following functional equation. So we have c of x times x squared minus c of x plus 1 equals 0. Okay, great. Now we can go ahead and just use the quadratic formula to solve for c of x. And let's see what we get. So notice we'll get c of x equals, so it'll be negative b, so that's going to be 1, because notice b is minus 1. And then we have plus or minus the square root of b squared, so that's going to be 1, minus 4 times a times c, so notice that's going to be 4 times 1 times x, so that'll be minus 4x all over 2a, so notice a in this case is x, so we get c of x equals this. Okay, great. Now we want to really figure out, well, what do I take here as the sign? Do I need to take the plus or the minus? Which one is going to make sense? So let's notice that we have 1 is equal to c of 0. So that's given in the definition of the Catalan numbers. But that should be equal to the limit as x approaches 0 of c of x. So I wrote infinity, I meant x approaches 0 of c of x. So what we want to do is calculate that limit in each case to decide if we keep the plus or the minus. So let's do that. So let's do the limit as x approaches 0 of, so let's do the plus first. So we have 1 plus the square root of 1 minus 4x over 2x. Okay? So notice at the moment, if we plug x equals 0 into this, we will get 1 plus 1 on the top, so we will get 2 in the numerator, and we get 0 in the denominator. So this is in fact a limit that does not exist. I think from the right, this is going to obviously go to positive infinity, and from the left, this is going to go to negative infinity. So either way you do it, this does not exist. So that gives us a lot of motivation that this should not be the plus sign, we should have the minus sign here. But let's go ahead and check that via the limit carefully. So let's go ahead and do the limit as x goes to 0 of 1 minus the square root of 1 minus 4x over 2x. But now notice we have an indeterminate form, so if we plug x equals 0 into this, we'll get 1 minus 1 over 0, but that's an indeterminate form. We could use L'Hopital's rule, but let's do it a different way. Let's maybe multiply by the radical conjugate. So we have 1 plus the square root of 1 minus 4x, 1 plus the square root of 1 minus 4x. So we've got something like that going on, but notice that's going to give us the limit as x goes to 0. So we've got something like a difference of squares in the numerator. So that will give us 1 minus 1 minus 4x over 2x times 1 plus the square root of 1 minus 4x. Okay, great. But now notice we have that 1 minus 1 will cancel to 0. And then this minus sign is going to distribute through to make this a plus sign. And then this 4x and this 2x will cancel to give us a 2 in the numerator. Okay, great. But now as we send x to 0 here, we have 2 in the numerator and we have 2 in the denominator. And so that'll be 2 over 2, which is 1. Which is exactly what we need it to be. So we can go ahead and erase this question mark here of plus or minus and put the minus in because that's what we have. Okay, so I'll clean up the board and then we'll pick up at this point and expand this as a power series using the binomial theorem. So in the last board, we argued that the generating function for the Catalan numbers are given by 1 minus the square root of 1 minus 4x over 2x. So I've rewritten it slightly. I factored this 1 over 2x out front, and then I have 1 minus the square root of 1 minus 4x. And now I just want to point out that here I'm going to use the following. So I will use that 1 plus u to the alpha, where alpha is really any complex number, can be expanded as a infinite series as the sum n equals 0 to infinity of alpha choose n times u to the n. Okay, great. So that's the binomial theorem. So I know, like, I proved some things that are maybe like a little simpler than that. I could have proven that, but we'll just take that as a fact. Okay, so let's see how we can use this. So now I'm going to go ahead and rewrite this as 1 over 2x, and then 1 minus 4x to the half power. Okay, which means I can use this binomial theorem with u equal to minus 4x and then alpha equal to a half. So let's see what that gives me. So that's going to give me 1 over 2x times 1 minus, now we have the sum n equals 0 to infinity of 1/2 choose n, so that's like my alpha choose n, and now u to the n, so that will be minus 4x to the nth power. So now I want to simplify this a bit. Okay, so now I'm going to use this thing that we proved earlier to rewrite our 1/2 choose n, and let's see what we get. We get 1 over 2x, 1 minus this sum n equals 0 to infinity, and then we'll have minus 1 to the n plus 1 over 4 to the n times 2 to the n minus 1, and then we have the central binomial coefficient 2n choose n, and now we'll have minus 1 to the n times 4 to the n times x to the n. So that's from breaking up this minus 4 times x all to the nth power. Now I'm going to do one more thing. I'm going to take this minus 1 to the n plus 1. I'll take one of the minus 1s and use that to turn this minus sign out front to a plus. And now let's see all of the stuff that can cancel. So notice that this minus 1 to the n and this minus 1 to the n are going to cancel with each other. This 4 to the n in the denominator and this 4 to the n in the numerator are going to cancel, which allows us to rewrite this thing as 1 over 2x, and now we have 1 plus the infinite sum n equals 0 to infinity of, let's see, we have 1 over 2 to the n minus 1, and then 2n choose n x to the n. So I'm going to go ahead and bring this to the top of the board so we can finish it off. So let's see where we are. We have c of x equals 1 over 2x times the quantity 1 plus this infinite sum. So we have n equals 0 to infinity, 1 over 2 to the n minus 1, 2n choose n, x to the n. So now what I want to do real quick is pull out the n equals 0 term to see what it is. So the n equals 0 term, notice we'll have 1 over 0 minus 1, so that'll be negative 1. 0 choose 0 is 1, x to the 0 is 1, and so the n equals 0 term is negative 1. So what that tells us is that if we take this n equals 0 term out, we can change this to starting at 1, and then this negative 1, which we have to take out, will cancel this positive 1 out front. Now we have 1 over 2x times the sum n equals 1 to infinity of all of that stuff. Now the next thing that I want to do is re-index. So I'll re-index so that n goes to n plus 1. And so that will move this index down so that it starts at 0. So let's see what we get for that. That's going to give us 1 over 2x. And then we have the sum n equals 0 to infinity of 1 over, so if I replace n with n plus 1 there, I get 2n plus 1. And then I have 2n plus 2, choose n plus 1, x to the n plus 1. But now some simplification can happen. I'm going to take this 1 over 2x, I'll take the 1/2 and I'll bring it inside and just put it in the denominator there. The next thing that I want to do is take this x in the denominator and cancel this x to the n plus 1 down to x to the n. But now we've got something that looks like our third bullet point that we proved. So notice we have 1 over 2 times 2 to the n plus 1, 2 to the n plus 2, choose n plus 1, and that's exactly the left-hand side of this, which means I can replace it with the right-hand side. So in other words, I can replace this with n equals 0 to infinity of 1 over n plus 1, 2n, choose n, x to the n. And that is my final closed form for the Catalan numbers, because let's recall that this is equal to the sum n equals 0 to infinity of cn x to the n. Okay, so I'm going to erase the board, put a summary up, and then do a nice little application of a new combinatorial identity. So as a summary, we calculated the closed form for the generating function for the Catalan numbers was given by 1 minus the square root of 1 minus 4x over 2x. Then we expanded that using the binomial theorem, and that gave us that the closed form for these Catalan numbers is given by c sub n is equal to 1 over n plus 1 times the central binomial coefficient 2n choose n. So notice here we can see this like nice quick application. And let's say we had the goal of finding the sum as n equals 0 to infinity of cn over 4 to the n. But notice that that is exactly equal to the sum n equals 0 to infinity of cn x to the n, where we set x equal to 1/4. In other words, this is c of 1/4, where c of x is given by this thing up here. So notice that is going to be equal to the square root, that's going to be equal to 1 minus the square root of 1 minus 4 times 1/4 over 2 times 1/4. And I should say that this is dependent on the fact that 1/4 is within interval of convergence of this function, but it is. You guys can check that if you want to. But notice that this all simplifies down to just the number 2. So I think in the future, me and the other channel, Professor Omar Math, are going to do more of these collaborations. So if you want, you can stick a comment either on this video or on the part 1 video of something you might like to see the two of us tackle. Okay, this is a good place to end the video.